get a book.
Regarding the question about homework 2, I can answer them later after the lab. So,
Okay. And also another question. For tomorrow, we have a quiz.
mhm,
And I remember the professor told us the end of the class uh,
mhm.
about which area we have a quiz, but I don't get it. What area I need to study? Is it possible just explain us more clear which area we need to study, or just give us some example? Uh,
I think she wants you to study the recurrence tree. So I'll discuss some examples from that area.
okay, thank you. Because it's
Recurrence
not
tree.
clear for me. It's tough. I didn't get it. What's happening and what we should need to do.
Okay. Mhm.
And I'm a little bit stressed because of the tomorrow. But appreciate it for that.
Okay. So first of all, I will discuss the some of the questions from homework 1. Okay. So first of all, the runtime of bubble sort. So I think many of you have confusion in that area. So the bubble sort algorithm is. Can you see my screen? Is it clear?
Yes.
Okay. Thank you. So the bubble sort algorithm is for I equals to 1 to n. We have another for j equals to n down to I plus 1. And then if a j is less than a j minus 1, then exchange aj with aj minus 1. So there are basically 3 lines. This is the first line, this is the second one, and this is the third one. So the cost for them, we will assume that they are C1, C2, and C3. Then the runtime for each of the lines will be, the first one will be n plus 1. So do you get why it is n plus 1? Any confusion, guys? Why the runtime for the first line is n plus 1? Can anyone explain how it is n plus 1?
Yes. We just do it n time and the plus one because we want to check it that one is work, that kind of things, and after that they go out of the loop.
Yeah,
It is
exactly.
natural.
Yeah,
Sure.
yeah. This loop will run n times, and then after n, it will become n plus 1. Then also we have to check that whether it is working or not. So that's why it will run n plus 1 times. Okay, then for the next line, the cost is summation I equals to uh, 1 to n, I, sorry, I. So can anyone explain why it is this thing, summation I equals to 1 to n I? Okay, so let me explain. So when I is 1, so the inner loop will run from n to I plus 1, means n n minus 1, n minus 2, down to I minus 1. And then As I increases, so this thing will change. So the in total, this inner loop will run, and first, so for the first iteration, it will run n times. Then for the second iteration, it will run n minus 1 times. Then n minus 3. In this way, it will run. For the last iteration, when I is yeah n minus 1, then it will run 1 times, and when I is n, it will not run. So that's why we will get this series as the number of times this inner for loop will run. Is it clear? As I increases, this inner for loop will decrease. Number of times this inner for loop run will decrease. So is it clear why we have this summation for the runtime of this inner for loop? Okay, so for the
Excuse
next line, yeah, questions?
Yes, these things happen because the second loop rely on the previous loop. Yes,
Yeah, exactly. Mhm.
but if not, that one is different. It's kind of n that n in n plus one.
Yeah, yeah.
No I.
But this inner for loop will always depend on the outer for loop.
Uh-huh.
Yeah, because we have this here, I plus 1 and 2 I plus 1.
Yeah, I got it. Thank you.
Okay. And for this third line, where we exchange the values, so that one actually its value will depend on the input array. Yes, so for the worst case, we will assume that it is the input array is sorted in reverse order, means we have to execute this line every time we encounter any aj or aj minus 1. For the worst case, it will run again summation I equals to um, 0 to n minus 1 I time. So this is for the worst case. And yeah, so the overall runtime for this algorithm will be total will be C1 times n plus 1 plus C2 times the summation equals to 1 to n I, and then C3 times the summation equals to 0 to n minus 1 I. Okay, so yeah. So now we'll just put the values for the summations. C1 times n plus 1, then for the next one we have n times n minus 1 divided by 2, and no, n times n plus 1 divided by 2. Then for the last one we have C3 times n times n minus 1 divided by 2. So solving that we get n plus C1 C2 C2 n square plus n divided by 2, and then C3 n square minus n divided by 2. So this will come out to be
I'm sorry, I have a
yeah.
question.
Mhm.
How did you get how did you solve for the summation? Instead of having the
Oh,
summation of I, you ended up having n times n plus 1.
yeah. So this is the formula that we have discussed in the first class.
Oh,
Yeah,
okay.
yeah,
Got
in the
you.
first class.
Thank you.
Yeah, yeah. Okay. Okay, so these two, we have the formula for the arithmetic progression. So sum of any series for the first n natural numbers will be 1 plus 2 plus up to n. This one will be n times n plus 1 divided by 2. This is the formula for the sum of any series. Is it clear? Okay. So by using this formula, we get the get the sum for those two summations. Okay. So if we solve that equation, we'll get half times C2 plus C3 n square plus C1 plus half of C2 minus half of C3 times n plus C1. So we can see here, this is the highest degree term in this equation. So the runtime will be big of n square. So is it clear how we are getting the runtime big of n square for the bubble sort algorithm?
Uh, yeah, it's making a lot more sense. I do have a question though.
Yeah, yeah.
How do you know when to use summation?
Because it depends on this runtime. So depending on that runtime, as we are getting it as a arithmetic series here, so that's why we are using summation. It will depend on the algorithm. Is it clear?
I'm sorry, I'm not quite getting it. So there's no certain way to know when to use summation. You just kind of have to know.
No, no. So for this inner for loop, as I have shown earlier, when I is 1, so it will, this inner for loop for j, this will run for n, then n minus 1, then all the way down to 2, right? So, and also it will run once more to check that whether the condition is correct or not, right? So it will run from n down to I. Is it clear what I am saying here?
Yes.
Mhm. Yeah. So if you put the value of I from the outer for loop, so when I is 1, this inner for loop will run from n down to 1, right? So that's n times. Is it clear how we are getting n times here for the inner for loop? When I is 1, we will get from n down to 1. So there are n times that inner for loop will run. Does that make sense?
Yes. Yes. That makes a lot more sense. So we would only count it for that and not everything else that falls in the for loop, right?
Yeah, exactly.
Okay.
So
Okay.
when n is 2, yeah. So this inner for loop will run n minus 1 times. So does that make sense? Because it is running from n down to 2, so we have n minus 1 numbers there. Is it clear how we are getting n minus 1?
Yeah, it's making more sense. Thank you.
Yeah, yeah. So in this way, if you progress, then you will get one series which will look like, for the inner for loop, we'll get one series which will look like n comma n minus 1, n minus 2, all the way down to 2, 1. Is it clear how we are getting this series?
Yes, thank you.
Yeah. So we are representing this series as that thing, summation I equals to 1 to n I. Do you see how we are getting that? Is it clear?
Yes.
Okay. So similarly for the inner, for the line 3, C3, we will get something like that. We are assuming that this is the worst case runtime complexity, so we have to execute everything. So this for loop will run one time more for every I, as we have to check that whether j is still valid for after I plus 1. It will run once more for I. Is that part clear? But this inner section, this if part, it will not run once more because it doesn't have to check whether the I is still valid or not. So it will run I minus 1 times. Means it will, for the first iteration, it will go from I down to 2 when I is 1, and then from n to n to 3. In the general case, it will go from n down to I plus 1. So there will be n minus I minus 1 numbers in all of those cases. Means first when I is 1, we have n minus 1 numbers there. When I is 2, we will have n minus 2 numbers. In this way, we will get down to 0, as it doesn't have to check whether I is still valid or not. So that way we will get a series which will look like n minus 1 plus n minus 2 all the way down to 0. Is it clear how we are getting this series for this if condition?
Yes.
Okay. So that's why we represent this as the form of this summation. Any other question regarding this runtime of bubble sort? Okay, so let's move on. Yeah, so I think all of you answered that one correctly. The runtime of an algorithm A is at most big omega of n cubed doesn't make any sense. That was correct. And yeah, the now question number 3 was also correct for most of you. For question number 4, let me discuss question number 4. So you have to order the following 16 functions by asymptotic growth rate from lowest to highest. If any of them are of the same order, then circle them on your list. Okay. So the functions were n plus 2 log n, then 7, then 5 n plus n square, 3 log n, log n square, n to the power 1/3 2n square minus 5 plus n to the power 4, 3n plus n log n, and then 7n square, 2 to the power n, 3 to the power 3 to the power n, 3 to the power n plus 1, n factorial, square root of n to the power 2.01, then 4 to the power log n base 2. So for all of those functions, we get 7 is a constant. So we represent it as theta of 1 as it will remain constant for any x. It will not change as it is independent of x. Then we have 3 log n and log n square, as log n square is 2 log n. So they have the runtime of theta log n. And then we have n to the power 1/3, then square root of n as to the power half. So 1/3 is less than half. So this function n to the power square root of n will grow faster than n to the power 1/3. Then we get n plus 2 log n. It will have runtime of theta of n because this is the highest degree term of n in this equation. And then we have 3n plus n log n. Here, this term is the highest degree term of n, as it will go faster than the 3n as n increases. So the runtime of this one is theta of n log n. Then we get 4 to the power log n base 2. It comes out to be so this is one property for the log where you can exchange them. So this one is basically n squared. Okay. Then we have another function 5n plus n squared and also 7n squared. So all of them has runtime of theta n squared. Then n to the power 2.01 will have higher growth rate as 2.01 is greater than 2. Then we get 2n squared plus, 2n squared minus 5 n plus n to the power 4. It will have runtime of theta n to the power 4. Then comes 2 to the power n, as it is exponential function. So these functions were polynomial, and this is exponential. So exponential always grows faster than polynomial. Then we have 3 to the power n and 3 to the power n plus 1. So this one is basically 3 times 3 to the power n. And all of them will have runtime of theta 3 to the power n. Then finally we have factorial. So runtime of the factorial will be highest among all those functions. So is it clear? Any confusion? Questions regarding the runtimes?
It's clear.
Mhm. Okay. Okay, so I think those two were the main questions where many of the students were confused. So now let's discuss the recursion tree approach to solve the uh, two equations. Okay. Okay, so first of all, let me give you two equations and you guys try to solve them using the master theorem. So do you remember the master theorem or do I have to revise it once again?
I think we have it.
Okay. So the first problem is this one where C is some constant. So I'll give you 5 minutes to solve that and then we will discuss the answer and solve it using recursion tree. So we will meet here in 1:38 again. Welcome back, everyone. So, anyone want to discuss the solution? What is A, what is B, and what is D?
Can I say?
Yeah, sure. Go ahead.
Okay. The A is 3, the B is 3. That means the log 3 into that means is 1.
Yeah.
And the D is 1.
Yeah, exactly.
That means it's equal.
Yeah,
And when it's equal, the answer is ND log AB. That means N log N.
yeah, exactly. So the answer is big O n log n. So now we will solve this using the recursion tree approach. So
Excuse me, in a tomorrow quiz, we need to do the recursion tree.
yeah, I think so.
Okay.
Okay. Yeah. So yeah.
I thought we were only supposed to give the function for it.
Yeah.
The relation, I mean.
Yeah, you have to solve it using the recursion tree. And I think you cannot use the master theorem directly for tomorrow's quiz. Okay, so
Somebody asked if like you could show the
yeah,
problem. Sorry.
yeah, as the recursion tree, yeah, that's what I'm doing now. So let's try to solve it using the recursion tree. So the given function is t of n is equals to 3t n divided by 3 plus c of n. So if we consider t of n divided by 3, then we will get 3 times t of n divided by 9 plus cn divided by 3. So is it clear how we are getting t of n divided by 3?
Why you do T N divided 3?
Because we have n divided by 3 here in our original equation. Is it clear? Any other question? How we are getting these terms? Kevin says yes. Anyone else? Any other question? Okay, so next we will try t of n divided by 9. So it will be 3 times t of n divided by 27 plus c times n divided by 9. So we replaced n with n divided by 3, then it with n divided by 3 times n divided by 3. So is it clear how we are progressing?
Excuse me, could you open that kind of things why you get 3T N divided by 9 plus C divided by 3?
Yeah, so if you put n divided by 3 in place of n, then, okay, let me show you that. So in this equation, we will put n divided by 3 in place of n. Then we will get n divided by 3, this entire thing divided by 3, plus c of n divided by 3. So this will become n divided by 9 plus c of n divided by 3. Is it clear? Yeah, how we are getting those terms. Any other question? Okay, so can anyone tell me what will be the next term? What will be the next value of, what will be the next term in this progression? After n we got n divided by 3, then we used n divided by 3 times n divided by 3. Now what will be the next term? Anyone has any idea? Yes, exactly. It will be n divided by 3 times n divided by 3 times n divided by 3. Sorry, I made one mistake here. N divided, yeah, this is not correct. Let me correct my mistake. So second term was n divided by 3 times 3. The third term will be n divided by 3 times 3 times 3. Yeah. N will not change. The denominator will only change. Okay, so after that, what will be the next time? Anyone has any clue? Yeah, exactly. It will be n divided by 3 times 3 times 3 times 3. Okay, so we can generalize it in the form that after n divided by 3 to the power 0, we got n divided by 3 to the power 1, then n divided by 3 square, followed by n divided by 3 cube, so on. So if we draw the tree for this one, we will get so our equation was t of n is equals to 3 times t of n divided by 3 plus c of n. So we can represent t of n will be c of n plus 3 t of n divided by 3. So we are getting 3 branches because we have the factor 3 here. If it was 4, then we would have gotten 4 branches. Is it clear?
Yes.
Okay. So then we will progress again in that tree. So we'll replace each of these t of n divided by 3 with their values that we have obtained here in this equation. So by replacing them, we will get something like this: c of n, then c of n divided by 3, c of n divided by 3, c of n divided by 3. And each one of them will have 3 sub branches with t of n divided by 9, t of n divided by 9, t of n divided by 9. So each of them will have those 3 sub branches. Okay. So after that, if we construct the entire tree, and we will get something like that. So at the first level we have c of n, then the second level we have c of n divided by 3, and again c of n divided by 3, c of n divided by 3. Then in the next level we have c of n divided by 9, c of n divided by 9, c of n divided by 9. So in this way, if we progress, we will get level and the number of nodes. So in the level 0, we have only one node. that is 3 to the power 0 for this level. And for the next level, we have 3 to the power 1 nodes. And for the second level, next level, we will get 3 to the power 2 nodes. So is it clear how we are getting the number of nodes and the level? Is this part clear?
Yes. Also, you're starting to sound a little muffled.
Oh, okay. Is my voice clear now?
Yes, you sound good.
Okay, okay. Okay, so yeah, for the level 2, we will get 3 to the power 2 nodes in this way. If we progress, then for the third level, okay. Can anyone guess how many nodes will we have for the third level?
3 cubed.
Yeah, exactly. That level we will get 3 to the power 3 nodes. And in this way, for the general case, we'll consider for the ith level, we will get 3 to the power I nodes. Okay, is it clear how we are getting this 3 to the power I at the ith level?
Yes.
Okay. Then we will assume that n divided by 3 to the power h, some constant h greater than 0. This thing is equals to 1. This is our assumption. H is greater than 0. So we will get from here 3 to the power h is equals to n, and then h is equals to log of n base 3. So is it clear? Is this part clear? How we are getting this one from that equation? Is the basic property of log. Any question regarding this one? Okay. So for the
I'm sorry.
yeah.
Just to verify, you got
Mhm.
3 of h is equal to n because you just multiplied the 3 of h put to both sides, right?
Yeah, exactly. Mhm.
Okay, and then you just use the log rule to get the log of n.
Yeah, yeah, exactly.
Okay.
Okay, so if we put h in this equation, then we can write that for the hth level, we will have 3 to the power h nodes. Is it clear? Because we already generalized this number of nodes for the ith level. So for the hth level, we'll get 3 to the power h nodes. Any question regarding this part? Okay, so then we will have t of 1, t of 1, so on. And we will assume that the algorithm will stop after reaching t of 1 because it is independent of n. So there will not be anything after that. Okay. Any question regarding that?
So for that, it's just t of 1.
Yeah, we'll assume that the algorithm will stop after reaching g of 1 in each of the leaf nodes.
Okay.
Mhm. Okay. So in this part, if we consider level sum, we'll get for level 0, we will have only C of n, Then for the level 1, we will have 3 times C of n divided by 3. So as you can see in level 1, we have 3 nodes and each of their values are n divided by 3. So that's why we get 3 times C of n divided by 3. Is it clear how we are getting this part?
Yes.
Okay. So this one will come out to be C of n, right? If we cancel both 3's, then it will be just C of n. Then for the level 2, similarly, we will get 3 squared times C of n divided by 9. Because here we have 3 square or 9 nodes and each of their values are C of n divided by 9. So again, we will get C of n. Then for the ith node, we will also get 3 of I, and then each of their values will be C of n divided by 3 of I. So for the ith node, we will get 3 to the power I divided by C of n divided by 3 to the power I. So again, this one will be just C of n. So similarly, for the last level of the tree, we will get 3 to the power h times C of n divided by 3 to the power h. So yeah, no, we cannot write that. This will be incorrect, as this term is t of 1. So we will get 3 to the power h times t of 1. So is it clear up to here how we are getting this much? 3 to the power I times C of n divided by 3 to the power I? Any question or confusions regarding that part?
No.
I'm sorry, can you show us where we got the C of n over 3 of I again from?
Okay, so if you see in level 1, we had 3 of 1 nodes and each of their values were C times 3 of n, C times n divided by 3.
Oh, so we just carry the first level down to the bottom.
Yeah, exactly.
Okay.
Similarly for the second one, it was that. And for the ith one, it will be similar to those top levels. We C of n divided by 3 to the power I. Is it clear?
Yes, thank you.
Okay.
I got a question.
Yeah, go ahead.
So, okay, let's say for instance, instead of having C of n as a second term in the function, what if it was just a constant like C and there was no C, no n? How would you
Yeah,
solve?
then it will be just C. Then you will not have this n here.
And then still follow the
Yeah.
same steps or no?
Yeah, you will follow the same steps, but you cannot cancel out this 3
Okay.
or whatever in those terms. They will carry all the way down to the bottom.
Right. Okay.
So it will the main part of the algorithm is just following those branches of the tree or the levels of the tree, but the values will depend on the equation or the function that is given to you. The basic algorithm is that you have to follow the levels and get their sums, but those sums will depend on the values of those functions that are given to you. Is it clear?
Then, for example, instead of getting right there in the middle, n divided by 3, what if you get something like n minus 2 or anything like that?
Yeah, then the tree will depend on that function. That will be different. Then you cannot apply Master's theorem directly on this one.
Oh, okay, I get you.
Yeah, okay. So let's continue. So for that one, yeah, we get this part. So then we can summarize this as t of n is equals to 3 to the power h times t of 1. As we get something constant here, so we cannot remove this factor 3 to the power h from this last level. Is it clear?
I'm sorry. What did you mean about getting the constant?
Because these t of 1s are not, they don't have n. They don't have n there. So we cannot replace them with something else. So we assume that they are all constants. They are producing some value. Suppose they are printing something. Print I, suppose, something like that. So they will just print something and stop. And they will not produce anything, any other level after that.
Oh, okay, got it. So for that, would it just be that? That would be the answer.
Yeah, so you have to find the runtime. Or she might ask, find the number of times the algorithm will print something. So for that, each of these levels are printing something, but you also have some other factors in the higher levels. So the runtime will also depend on that, along with this one. So is it clear?
I see what you mean. Is that something we have to worry about right now?
Yeah, no. You just have to see how this recursion
Okay.
tree method works.
Okay, thank you.
Okay, so for the last level, we have 3 to the power h times t of 1. Then for the all higher levels, we can summarize them as summation I equals to 0 to h minus 1 c of n. As we will stop the level before h, uh, we cannot remove 3 to the power h for the last level only. For all the other levels, we can just remove that. So it will, and as you can see here, for all the levels, we get C of n. So from this one, we are getting the summation here. We'll get C of n for all the levels from 0 to h minus 1, and we will get C of n for all of those levels. So is this clear how we are getting this part?
Did you get h minus 1 because of t of 1?
Yeah. So we assume that at level h, we are getting t of 1. So for the all other levels above that, we'll get C of n, something like this one. We'll just replace this I with h minus 1. Is
Okay,
it clear?
thank you.
Okay. So then if we replace this equation, then we'll get t of n is equals to 3 to the power h t of 1 times summation h minus 1 c of n I equals to 0 to h minus 1 c of n. So as c of n is independent of the I, so we will get c of h times t of 1 plus h times c of n. So is this part clear? Any questions regarding this one?
You just use the formulas from the beginning, right?
Yeah, exactly.
Okay.
Just summation of this one. It will be h. Yeah, as it is independent of I. Okay, then we will replace this h from our assumption, which is the, here. H is equals to log of n base 3. So if we replace this h in this equation, then we'll get 3 to the power log of n base 3 times t of 1 plus c of n times log of 3 to the log of n base 3. Okay. So then we will get, if we simplify this, then we'll get n times t of 1 plus c of n log n base 3. So here we have this term as the highest degree term, as it will go faster than n. So then the runtime of this algorithm will be big of n log n. Is it clear how we are getting that? This equation?
How did you get the 3 to the log of n?
Yeah, we replace this h. You remember we assumed that
Oh, I'm sorry.
this n is
Yes.
1.
Okay.
Yeah, so just by replacing that here, we get this part. Then just by solving it, we get that the highest degree term in this equation was this one, c times n log n, as we assume that c is greater than 0. So the growth rate of this part will be higher than that part. So therefore, the runtime of this algorithm is big of n log n. Any confusion? Okay.
Excuse me.
Yeah, go ahead.
Did you go to the top?
Mhm.
Yeah. No, not too much. Just go down. Just go down.
Okay.
No, down. Okay, here. The Tn is 3 to power of the h, and after that, in a summation, it's kind of I0 to h minus 1. Why h minus 1? Why is not h?
Yeah, because we assume that at the level h, we are getting t of 1, right? This was our assumption.
Uh-huh.
So for this term, the general term of this tree, it will only work up to h minus 1, the level above that, right? For the h level, we can say that.
Thank you.
Yeah. So that way we get h minus 1 here. Good question. Any other confusion, guys? Okay.
Can you stop right there real quick?
Yeah, sure.
Um,
Yeah, I will publish these notes in the Canvas, so don't worry about that.
okay, yeah. No, I was just looking at what you did right there with n divided by 3h.
Yeah, okay.
Okay. Got it.
Okay. So any other confusion how we are solving this? So it will work for any equation. So the general process is similar for solving any t of n. You just have to follow these rules and create the tree. And then you have to assume that for some h or some other variable of your choice, this thing is or that part is equals to 1. This part becomes 1. It will depend on the equation that is given there. You have to assume that, and according to that assumption, you have to find the final formula for the summation of all the nodes in that tree. Then from this equation, you just put the value of that variable age in terms of n, and then you get the answer. This is the general procedure for solving all the recursion trees. Is it clear?
Yes, but this one is very easy. Could you just
Yeah.
explain something a little bit harder, because that one is very
Yeah,
easy.
okay, so let's assume, try another one. Okay, for that one, we will assume that the function is t of n. Okay, let's assume this one real quick. T of n is equals to 3 t of n divided by 3 plus n square. Okay, so
Excuse me,
here, mhm.
could you explain something we cannot answer with the master theorem? Just we need to solve it with the tree.
Mhm.
Because all of them we can answer with the master theorem. It's much easier to just solve it with the tree, but we can do this a little bit more complicated.
Okay, let me see whether I can find some example.
Thank you.
So, maybe in the next lab, because we have just 4 minutes left in this lab.
That's fine.
Okay, so I will look for some other example, and then maybe we can discuss it in the next lab. Okay. Any other question, guys? Regarding the tree approach, recursion tree.
Excuse me.
Yeah, go ahead.
Yeah, I have a question, please. Regarding the assignment, homework 2.
Yeah.
So there is a question exercise, I think 2.4 in page 71, right? But the version that I have, it's in page 83, I think. So
Have
I'm
you
not-
checked for the correct volume of the book?
Yes, please.
Yeah. Have you matched the correct volume?
The current.
So I think she needs the latest volume of this book.
So someone wrote it in the, yeah, this is the question that I got. Someone wrote it in the chat,
Mhm.
the question. So this is the question that I got. I'm not sure if that question that we have to solve. So yeah, the volume that I have, it has its, and the exercise is 2.4, but it's in page 83. I'm not sure if they are the same. Just to make sure that.
Let me see.
Yes, I have the same problem because I don't know what actually question for exercise 2.4.
Okay, okay.
You just published that question in a Canvas
Oh, exercise 2.4, page 71. That one.
because
Mhm.
Okay, yeah, yeah.
we have
So yeah,
different version of the book and in different pages. It's kind of confused me. Which one
yeah.
is the question?
How about the first one, exercise 2.3, page 71? Do you guys get that? Or
No, we got that in page the same page, like 83, the page 83. You mean 2.3, right?
yeah, 2.3.
Yeah, it's in a for me it's in page 83.
Okay, 83. Okay. Yeah, so I will discuss with Dr. Rina and maybe we can publish those questions in the Canvas.
Yes, please.
Yes, it's perfect because I just kind of confused what is.
Yeah.
All right.
Okay. Okay. So yeah, I'll look into that. Anything else?
That's it.
Okay. Okay. So yeah, I think that will be it for our lab meeting today. And all the best for the quiz tomorrow.
For
See you
tomorrow,
again.
please, you give us some kind of the T and something get a book